We now start to talk about transistors and how we can use them to make amplifiers and to make logic devices and lots of other useful things. We'll first start with bipolar junction transistors, sometimes known as BJTs, but often just known as transistors. If people don't specify the kind of transistor, it's probably a bipolar junction kind that they are referring to. So a transistor of this kind is made from N and P doped semiconductors, just like a diode, except now there are two junctions, and you either go from an N dope to a P dope to an N dope, or a P to an N to a P, giving rise to the two kinds of bipolar junction transistors there are, NPN and PNP. So the PNP kind is shown here, and it has a symbol that looks like this, and there are three parts for each of the three types of conductors. The middle part we always call the base, and then the two side parts are the emitter and the collector. Now you would think this would be symmetric, but often so that we could replace the emitter and collector, but often the emitter is much more doped than the collector, so in fact it's not symmetric between the two. I should note that the base is always a very, very thin layer of whatever dope kind of semiconductor you have. So we have the three parts again: emitter, collector, and base. So in the symbol, the emitter always has an arrow on it, and the arrow shows what direction the current is going to flow, if current's going to flow at all. And the emitter will always emit the charge carrier. So in a NPN transistor shown here, the emitter emits electrons, and so the electrons are moving this way, which means the current is flowing that way. What the emitter emits, the collector collects, and the base then just controls how much current is going to flow by its own current. So we'll often deal with the NPN, as I've shown here, more than the PNP, but we should be able to do both. And so everything we need to know about it we can label with three currents and three voltages, and often we'll want the differences with voltages as well. The fact that there are three makes it complicated for IV characteristics, and so making sure we know what we're talking about in any case is useful. And so usually we'll label voltages and currents by the subscript. So the current that flows on the emitter we'll call IE. Likewise, the voltage on the base we'll call VB. And then to describe the difference in voltage between two of the leads, we'll talk about VEB, which is VE minus VB. Likewise, for any combination, it's the voltage of the first subscript minus the voltage of the second subscript. So the first thing to realize about a transistor is that if you connect directly the collector to the base, it works just like a diode. It in fact is a diode, but it will always have an N equal 1 in the exponential, unlike the case for a silicon diode where you have N equals 2. And so you get that the current flowing from the base to the emitter in this NPN version works just like a diode. It turns on at a voltage of about 0.6 or 0.7 volts. So when we're not diode connected, the key to understanding the transistor is to look at the collector-emitter IV characteristic, which I've copied out of the book here. And basically, so when you have a large enough collector-emitter voltage above some very small voltage, basically you get a current source there. So no matter what the collector-emitter voltage difference is, you get a current that flows, but that current that flows is controlled by how much current is flowing on the base. and if we and the collector emitter current, the collector current, but it almost all goes to the emitter, is very much larger. So notice that if we have a small current of 20 microamps on the base, we have a current of 3 milliamps for this particular case on the collector. So 100 times larger, 150 times larger. We describe the voltage regions. There's 3 for a transistor. So if the voltage between the collector and emitter is large enough, we're in the active region as long as there is current flowing on the base. If the collector-emitter voltage becomes small, we're in a saturation region. And then if there's no current flowing on the base, meaning the base emitter voltage is too small, we're in the cutoff region, which means that it is not working. There's no current flowing at all. So this is the diagram that allows us to understand what's going on in a BJT transistor. So we're going to model what goes on in the active region with 2 models. They're almost the same. We just move some parts around. So because in the active region, the current is independent of the voltage between the collector and emitter, we think of another case where voltage is the current is independent of the voltage, and that's a current supply. So, but in this case, we can change the current with the base current, so it's a dependent current source, which I've drawn here, and that direction of that current depends on whether it's an NPN or a PNP, as I've shown. So in a PNP, the current flows out of the collector. In an NPN, it flows into the collector, and it's some factor in this first model, the alpha model, it's some factor, very large, close to 1 factor of the current that flows on the emitter. So in the PNP case, we have a current that flows this way, and a little bit gets taken off. But most of it, alpha, flows through, and in the NPN case, we have a current flowing from the collector to the emitter. The second thing is that there is basically a diode drop between the emitter and the base, and we draw that diode on the emitter because we want the current. We're worried about this current mostly, so we draw everything on the emitter. And so this is really just one diode with a diode drop of 0.7. Here I've drawn an ideal diode. And so as long as the emitter base, if we have current flowing, we know that the emitter base voltage will be 0.7 from the diode, but the current can only flow this way in the PNP. Likewise, here we have to have a base emitter voltage of 0.7, and the current can only flow this way, and most of the current that's on the emitter flows through the collector, but a little bit, whatever doesn't flow here, goes out on the base in the PNP case, or in on the base on the NPN version. Remember, though, this is only for the active region that we can use this model. The second model is just for the active region, but here we're interested in how the current on the collector depends on the base current. And we use a different factor, beta, for this, and beta is a much larger number. A factor of 50 to 100 is common. And so we just move our diode from the emitter leg to the base leg. And again, that means we'll have the same voltage difference between the base and the emitter, given by this potential. And all the currents flow the same way. It's just that we're connecting the collector current to the base current rather than the emitter current. And so basically this says that a small current on the base, as long as it flows in the NPN case into the base, will control a much larger current on the collector, and it all comes out on the emitter. Like a diode, we'll want to be able to use a load line analysis. to understand how to use a transistor, say, in an amplifier. And so in this case, we'll put a resistor between some voltage supply and the transistor, and we'll connect the emitter to ground. So this is a common emitter kind of setup. Common emitter means you're connecting the emitter to ground. Common is another word for ground. And so what happens is that we put a voltage in on the base. That voltage creates a current that flows through RP. Some of it gets, and enough current flows that we reduce the voltage here, but as long as the voltage here is 0.7 volts above the emitter voltage, current will flow there, and a much larger current will flow here. That current will make there be a voltage drop between the voltage supply and the collector itself. And so as long as this voltage is big enough, then we're going to be in the active region. And as long as this current is small enough, this voltage will be high, above the cutoff region and will be in the active region. And so if we increase this voltage, we'll increase the current here, and that'll control how much current actually does flow here. If more current flows here, then we're higher up on this line, and the voltage will drop between the collector and the emitter. We can't make the current here so high that this drops below zero, so at some point we cut off, we saturate. That'll put us in the saturation region, and we'll get much less current than we expect. However, a current will always be flowing here. It's just that when we get into the saturation region, we've saturated how much current we can pull between VCC and ground. We can also use a transistor to make a NOT gate, where the input voltage is on the base, the output voltage is at the bottom of a resistor, who's then connected to ground. And so here we think if the voltage here is small, less than 0.5 volts, then there won't be any current flowing into this NPN transistor, so therefore we'll be in the cutoff region and no current will flow. If no current flows through this resistor, then there'll be no voltage drop across it, and V out will be the input, which here is 5 volts. As we increase this voltage now to much greater than 0.7 volts, with this 20K it has to be greater than 1.2 volts, then a current will flow here, and in fact that will be a large enough current to draw a lot of current through the 2K resistor. In fact, it'll draw enough to bring basically the 5 volts down to 0 here, or 0.2 there, and that's as low as we can get, and so that's close to the low level of V out. Now in between 0.5 when it's cut off and 1.2 where we draw so much we're in the saturation region, the voltage out depends exactly on how the current is, and that's when we're in the active region. But for digital circuits, for logic circuits, we want to avoid that region. And so you can see that here, this is how TTL often works. You have a low region for V out. It goes up to 0.4 or something like that, where you count it as 0, but it has a large region for high, because this just has to be above 1.2 to be counted as high on the input.